Today's lesson will be about graphing exponential functions, but only the beginning. The goal today is to graph the parent exponential functions, but you'll see in the three different objectives that we have here, one would be to recognize exponential functions, one would be to evaluate or to plug in exponential functions, and then we'll get to the graphs. So today is mostly about the basics about exponential functions. You can see the sub-objectives and the vocabulary at the bottom. So, can you recognize exponential functions? Well, this is an example of what's not an exponential function. This is a line in the form y equals mx plus b. Over here to the right, we see a new function. You can see that it's curved in a new way. This is either growing super fast or it is rapidly decreasing as it's going down. This is the general shape of what we call the exponential function. You can see the shape of the graph is that it starts out kind of slow, kind of flat, and then all of a sudden it has this rapid increase going up, up, up. Or this other one has a rapid decrease going super fast, falling so far, and then it kind of levels out and flattens. This is an exponential graph. Now, what about the linear versus exponential tables? So what we need to do is we need to ask ourselves, how are the x's changing over time and how are the y's changing over time? We can see that the x's increase by 2 and the y's decrease by 3 consistently over time. So we would say this is linear. It is linear because it is increasing or decreasing by a constant rate of change. We have a fancy vocab word for rate of change for lines, don't we? Called the slope. The slope is a change of y over change of x. So once you've already identified how the x's and y's are changing, you can express it as a simple slope. If you can make it a slope, you can call it a line. But again, the vocab is constant rate of change. That's the big thing here. Now let's look at an exponential graph, or a table that we don't know what it is yet. So we look at how are the x's changing and how are the y's changing. X's are clearly going up by 1, but then we check how are the y's changing. You might suspect that it's going up by 5. 5 to 10 is plus 5. Well, then I would expect that to be constant, like before, constant rate of change. So up 5 again would be 15, but that doesn't match what I see, so we have to try something else. What if we try multiplication? And we see that it is predictably going up by 2 every single time. Times 2, times 2, times 2, times 2. When it's consistently multiplied, we call it exponential. You know it is an exponential table when you can find the common multiplier. So when you multiply y's by a common number. The second objective for the day is to evaluate exponential functions at the given x values. Now notice all of these equations are in a certain form. Y equals some a number times some b number, we call that a base, raised by x. Has to be that way, can't be any other way. So my directions to you is follow the rules of PEMDAS, and this is really the plug it in directions. So we're going to follow PEMDAS, specifically exponent and multiplication, and my directions to you is that you will need to remember to do the exponents before multiplication. These examples are very predictable. You will have a number times a number raised to a number. So we're going to have multiplication and exponents. You're always going to do the exponents first. Let's see the first example. We're going to take this x value, and like I said, this is the plug it in. So we're going to plug it in for x right there. So when I rewrite it, I get y equals 4 times 2 raised 0. And we're going to do exponents first. So exponents says do that next or first, which is 4 times 1, because anything raised 0 is 1, which means my answer is 4. So let's try some of these together. Number 2 is different because it has a negative sign. Well, this negative is located all the way out front, so it's really an afterthought. What we need to do, same thing as before. You take this x, you plug it in for that x, And when you rewrite it, you remember PEMDAS, exponent, then multiply. Except now it's a -3 that I'm going to be multiplying. So the exponent that I'm going to do first is located here. I'm going to do 2 raised 2, which is a 4 with a -3 in front as an afterthought. Well, -3 times 4 is 12. Next, I'm going to keep going. Number 3 is very similar to number 1. I encourage you to pause now and try it yourself. This is the substitute or the plug it in step. Did you get that? This is what happens after you apply the exponent, which you do before multiplying. Did you get that? And 36 is my final answer. Number 4 is like number 2, but ooh, look at this. My exponent is actually negative. So as I'm writing this, I want you to think, what does a negative exponent mean? So as I rewrite this, I hope you're thinking, I remember my teacher's voice. The negative exponent means fraction bar. So I'm going to write the -2 because that doesn't have the exponent, right? The 3 has the exponent. So I'm going to make a fraction bar, and the 3 to the -1 is just regular or on top. So it goes to the bottom. When it goes to the bottom, it's not negative anymore. It's happy. It's positive, a +1. And we know 3 to the 1 is just 3. That's one of those easy identities. And that's my answer, -2/3. Now, it's okay that it's negative. We can have a negative number. We can't have a negative exponent. Number 5 is just like number 3, maybe also like number 2. So let's try that together. We're going to take the x, plug it in. I encourage you to pause and see if you get it right. And here I just adjusted the inputs here. We're going to use x of -2 and x of -3. These are going to be very similar to a combination of numbers 3 and 4. So give it a shot yourself. I'll reveal the answer as we go. So this is what it looks like after you plug it in. Next, we have to take care of that negative exponent. Think, what do I have to do with the negative exponent? If you said fraction bar, you're right. Now I have 4 over 3 squared. What is 3 squared? A 9, and nothing simplifies 4 and 9, so that's my answer. Number 6 is going to be the same. I'm going to take my x, plug it in. I'm going to pause and reveal the answer as I go. Try it yourself. That's what you get after you substitute. What do you have to do with a negative exponent? Remember, negative exponent means fraction bar. And when you move it, it becomes positive. Now I simplify 4 over 27. Nothing can simplify, and that is my answer. I have evaluated the function at each x. This slide has a lot of information on it, but I want you only to look at a couple things at a time. Do not look at any of this information. In general, an exponential equation is going to look like this, with some number in front, some number as a base, raised to an x power. Now, let me just let you know now, this a can be any old number at all, a decimal, a negative, I don't care. Just can't really be 0. The b needs to be positive. I can't see any negatives, and it can't be a 1. Those are two important things, positive and not 1. And then obviously this x needs to stay a variable. It needs to be an x. Now when we talk about the parent is always kind of more basic than any iteration of it. So we're going to take away this a, and we're going to have just the base raised x. So if you get something that looks like this, and you want to draw your parent function, ask yourself, what is the base? Remember, the b is what's raised to the x. It needs to be positive, it cannot be 1, and the exponent is the variable in the exponent spot. Now I reveal the bottom of this, not because I need you to write it down, I need you to focus on it, but if you wanted to, you have it in one place here. Generally, you need to identify the base that we talked about. Then you are going to make your table, graph the points, and then make your shape. And I also want to point out that this is the first time we're seeing this word asymptote. Now, this is a very odd, interesting new word for all of you. An asymptote is a line that the graph gets close to but never actually touches and never crosses over. we draw it as a dashed line because it's not part of the graph, but it is a guiding line. Think of it as a wall or a fence. The fence really defines which part of your yard is your yard or which part of the park is the park, and where past that fence, you never actually go. You don't go past the fence into the wooded area or whatever is outside of your yard or the park. Remember that the fence or the asymptote is the borderline of where your graph exists. So let's see some examples. Now the first type is when you have a base that is an integer. Now I put these here again, not because I need you to focus on them, but I'm sure you would appreciate seeing the steps here as I'm talking, and you could be reading as well. So we need to make our table. So we're going to make an XY table if it's not already there for you. And we're going to have enough space in the middle to show our work. Then we're going to have the same x's. We're always going to use the same x's over here. X of -2, -1, 0, 1, and 2. Always and forever when we're talking about parent function graphs. Now, we're going to do 2 times x. Now, we just did a lot of practice of plugging in an x. Now, I'm going to be smart here. Most people make mistakes when we get into negative, so I'm going to start where it's kind of easy. 2 raised to the 0. Now, raised to the 0 is one of those laws or rules that either you know it or you don't, and hopefully you do know by now. Anything raised to the 0 power is 1, and then 1. Anything raised to the first power is itself. Now is the first time where I actually have to do some math. What is 2 squared? Well, 2 times 2 is 4. Now I'm going to draw some curves here, and I want you to pick up on some patterns. But we're going to do the work. I just want you to see the patterns as we do it. Now this middle box is going to be really important for the negatives because we have to think about it. So I'm going to leave some space. 2 raised -1. Now remember, negative exponent, you better show me a fraction bar. And it's a big number, so it goes on bottom now, and the exponent becomes positive. And there's nothing on top, so it gets a 1 placeholder. And 2 to the first is just 2, so this is 1 over 2. Any patterns here? Let's keep going. This is going to be my base raised to the -2 power. So negative exponent, you better show me a fraction bar. It becomes 2 squared with a 1 placeholder. So 2 squared is 4, 1/4. And I need you to look at any patterns. I'm not going to tell it to you, but think about it. Now I added a little bit of notes over here. This is how we're going to set up this table. Always -2 through 2. Show your work in the middle. Answers go next. Now from here, I'm going to draw the ordered pair. Now the ordered pair goes x and then y. So what I'm going to do is I'm going to get this x with this y, and I'm going to write the pair -2, 1/4. I'm going to keep doing that. -1, 1/2, 0, 1, 1, 2, and 2, 4. So that was the draw 5 points. Next up, I need to draw the dashed, excuse me. So that was write the 5 ordered pairs, check. Step 2 is graph the 5 points. I'm going to graph these. Now I'm going to start with the big numbers here. 2, 4, 1, 2, 3, 4. 1, 2, 0, 1. And then we get to these things -1, 1/2. So that's kind of about there. And then we're getting real tiny, so tiny that I can't expect you to be that precise. But what I can expect from you is this. There is going to be, on all of these, there is going to be a dashed line on the x-axis. So when you're using Go Formative, you're going to take the line tool, make it dashed. I made it as straight as possible. I graphed my 5 points, check. I drew the dashed line on the x-axis. Now I'm going to draw a nice curve connecting the dots and hugging the dashed line. So I like to kind of go in the middle and then curve, middle and curve. So in this middle point, it curves up and looks like that. And then this way it curves down. Now watch carefully how I curve this. It kind of looks like a straight line after a while. So it hugs the dashed line. It stays above it and never goes underneath it, never actually even touches it. So that's what this vocab over here means. The horizontal asymptote, that's what this is. The horizontal asymptote is over here, and it's always going to be the horizontal line here of y equals 0. Okay. Now, oftentimes we're going to ask you to name a few points. I'm going to skip that for a minute. We would probably name the middle 3 points, which is over here in my table. We already drew the 5 points. But if I didn't already have the 5 points, then it would be over here, the 3 points. The next really important question to ask is it increasing or decreasing? So what we often do is we say, okay, well, what if I was a little green ant? And I was all the way over here, all the way to the left. And we always read left to right, right? So as this ant marches forward, not much is happening. But then he gets to the middle here, and is he increasing or decreasing? Is his height going to go up or down? Is he coming down from a mountain or going up to the mountain? And it looks like he's going to be going way up. So it's going to be increasing. Now, all this information is extra, right? I'm going to delete the things that are just kind of extra. So all of this is extra. 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 On a typical day, and I can't really quickly erase this, but in a typical day, all you're going to be doing is this stuff. That's it. That's the entire work. Let's try it again. Now I simplified these just a little bit. So the simplified steps is this. Identify the base, and for parent functions, the base is the obvious thing. The base is just 3. So it's going to be 3x is what I'm doing here. Check. I'm going to make your table, which I gave to you this time, and then check. But now I need to like do the table, right? So now I'm going to actually do it. So we always use the same x's. Do you remember what they are? Always the same. Now I like to start at 0 because it's always going to be the same. 3 raised 0 is 1. And then 3 raised to the first is another easy one to remember. It's just itself. And then many people can imagine, well, what happens if I square, if I multiply it by itself? 3 times 3 is 9. Then I look at the negatives. Now 3 to the negative 1 is not too bad. It means fraction bar, put it on bottom, make it happy, make it positive. And so my answer is 1/3. This one's a hard one. This one really is. But we've been practicing this enough. You should be somewhat familiar with it. So the first thing is fraction bar, put it on bottom, make it happy, make it positive. And then I need to think about, what is 3 squared? Well, it's a 9 on bottom. Now when you plot these points, you extract the x and the y, you get ordered pairs. We have now made our table. We're going to graph our points now. I like to start with 0, 0, 1. That's a pattern. It's always going to start 0, 1 in the parent function. 1, 3. It's another pattern since 3 is our base over here. And then the next one is up to 9. Now the next one, my preference is to then take my to make my asymptote here. Because now when I start getting these fractions, it gets real weird. Where's 1/3? It's a little less than a half. Where's 1/9? Oh. Where's 1/9? Super close to 0. And then what's the shape of this? Like that. And then I'm just going to hug just the top of my asymptote going that way. All right, now we're going to name the asymptote. The asymptote here is at y equals 0, because that's how you name a horizontal line. 3 points. We kind of have them over here already. And is it increasing or decreasing? Well, if I am a little ant over here, and I go this way, I'm eventually going way up, climbing the sky, increasing. Now we're going to do one where I don't have a simple integer as a base. What is the base? The base is 1/2. Well, this part doesn't change. I still have the same x's that I'm working with. I still write my function here, half raised x, and I still start at 0. What is 1/2 raised 0? Well, it's always going to be 1. And then when I take the 1/2 and raise it 1, I get itself. And if I take 1/2 and multiply it by itself, that's 1/2 times 1/2. That's 1 times 1 is 1, 2 times 2 is 4. And then when I take 1/2 and I raise it to a -1, that's like saying, well, flip it, 2/1. We don't write 2/1, we write 2. And then same thing here, 1/2 raised -2. I get 2 squared on top, 1 on bottom. That's just a 4. Extracting the ordered pairs, -2, 4, -1, 2, 0, 1, 1.5, 2.25. And now I'm going to draw it. Now notice what happens with this one. 0 and 1. If I go to the 1, I'm at a half now. Oh, well, now I need my asymptote, don't I? So then at 1, I'm at a half. And then at 2, I'm at a quarter, which is, even closer to 0, but not quite at 0, and definitely not negative. Then when I go to -1, I'm at 2. When I go to -2, I'm at 4. And when I draw a nice curve through these points, and I approach my asymptote to the right, and then it goes up and up and up and up and up, now I still have y equals 0. I already named a bunch of points over there. Is it increasing or decreasing? Well, as I'm an ant all the way over here to the left, and I go to the right, I'm going way down. So this is a decreasing function. We're going to call it decay. So here is the 3 graphs, the 3 functions on top. These are all y equals, and these are all their graphs, very simplified, and all like the 3 points, we all plotted 5, but these are just 3 middle summary points. And I want you to pause the video now and look for any patterns that you see. Patterns amongst these numbers, patterns amongst, is there any way that you can go from here to here, any shortcuts you could take, any patterns you could take? They exist. So I encourage you to pause now and look for it. First pattern, the hardest one to find, is the number. So the base appears always in the 1 position, 1 comma your base. That's one pattern. What do you notice? The second one in green, notice it's only down here. I don't care what the type of exponential graph it is, so long as it's just a parent function. Your second pattern is you're always going to have 0, 1. Because if you raise anything to the first power, it's always going to be 1. Nothing you could do to change my mind. The last pattern has to do with increasing versus decreasing. When are they increasing or decreasing? Well, the left 2 are increasing, the right one is decreasing. I want you to look at the parent function and see why. Any guesses? It has to do with the base relation to 1. Depends if the base is larger than or less than 1, but I need to change the one on the right. Let's see how it changes. The base needs to be between 0 and 1.